I'm Alan Rossiter, Executive Director for External Relations and Educational Program Development for UH Energy at the University of Houston. And I've been at the university just over a year. Before that, I worked for 2 major chemical companies, and I also spent a substantial part of my career in consulting, both with a small firm and then as an independent consultant on my own. My academic training, bachelor's, master's, and doctoral degrees are from the University of Cambridge in chemical engineering. And I am a licensed professional engineer here in Texas and also a fellow of the American Institute of Chemical Engineers. And I will be talking about Harvey and the beauty of the steady state. This Energy Forum is organized by the Texas Industrial Energy Efficiency Program. And you may wonder what Hurricane Harvey has to do with energy efficiency. Well, I'm sure there are a lot of different answers to that question, but the point that I mostly want to make is this. Chemical plants, oil refineries, all run best when they run under steady conditions. That means better production, better quality, and yes, also better energy efficiency. Any sort of disturbance or disruption will tend to make all of those parameters worse. And Harvey was one big disruption. And we'll talk about some of the implications of that during the course of this presentation. But for the moment, I think all of us who live in the Houston area, or certainly lived here during that time, have a Harvey story. And I'd like to tell you a little bit about mine. I was actually out of the country when the hurricane hit. Of course, I knew it was on the way because of the weather reports, but I didn't have any concept of the real scale or the impact that it was going to have. What really got my attention, though, was when I received a photograph in my inbox. Yes, that is the breakfast room in my house with 18 inches of water in it. And yes, that is a bicycle, which proves this must be the Rossiter residence. As it happens, that particular bike is my wife's, not mine, but you get the general idea. Anyway, once I had taken in what that picture was showing me and recovered from the impact, 2 thoughts crossed my mind. First of all, my wife has been wanting to remodel for a number of years, and now she's going to have her opportunity. And number 2, thank goodness we've got insurance. Well, I was out of town, as I said, in fact, out of the country, and I needed to get back home, so I tried to get the first available flight, though it took several days because the airport was, of course, closed after the hurricane. And when I did get back, I was actually on one of the first flights that was able to fly into Intercontinental Airport. As we were approaching the airport, it was a rather surreal experience because when I looked down, there were lakes where there weren't supposed to be lakes. And I also noticed a cluster of houses that seemed to be sitting at the side of canals. And from up in the air, it looked like they may have been transported from Venice, and it was a rather pretty little picture. But I'm sure if you lived down there, it was anything but pretty because those weren't canals. They were flooded streets. When I got back to Bel Air, where I live, the sight was also quite stark, quite striking. Outside virtually every house along my street, there were piles of debris. Looked a bit like a war zone. And Bel Air itself was one of the worst hit places. About 40% of the houses in the city got fairly severe damage. Our area in Bel Air, our subdivision, if you want to call it that, was hit far worse than that. It was much more than 40%. So it was not a pretty sight. But of course, the damage was not limited to our small part of the greater Houston area. The chemical plants, the refineries were hit pretty hard. The total cost of Hurricane Harvey has been estimated at about $125 billion. And looking at that chemical sector, the petrochemicals in particular, this little table shows you the impact that the hurricane had on plant capacity due to shutdowns. And you'll see there that if you look at some of the major petrochemicals, roughly 23% of the propylene production in the US was shut down as a result of the hurricane, rising to nearly 37% of the ethylene capacity. So those were huge hits on petrochemical operations throughout the US, but especially here in the Houston area and along the Gulf Coast. So, as I've said, steady state is good. How do we come to that conclusion? Well, I think this one equation really gives a big hint. And what this tells us is simply the definition for energy intensity, which is the amount of energy that you consume divided by your production. How much energy per unit of production. And so energy intensity rises, which really means efficiency falls when energy consumption increases or production decreases. And as we'll see in the next few slides, this almost always happens when your operations are unstable or your conditions are in some way abnormal. We started this presentation with my Harvey story, and then we got technical with the definition of energy intensity. I'd like now to lay out the agenda for the rest of this talk, and we'll start with some examples, some detailed examples of how energy intensity is affected by disturbances in the plant. First of all, looking at summer rainstorms as an example, and then talking about some throughput cut situations and the impact that those have. We'll then move on to some other situations more generally, and then move on to see how this applies in the case of Hurricane Harvey and other major natural disturbances that might occur. And then we'll wrap up with a brief discussion of some ways to mitigate these effects and have less of an impact on energy intensity. As we go through these examples, you'll see this little table come up a number of times. And here we're looking at the three parameters we talked about in our equation. First of all, the EC, which is energy consumption. Secondly is production rate, P. And then the third one, EI, is the energy intensity. And we'll be looking at how each of these changes in each particular example that we look at. The red obviously means a bad change. So energy consumption going up is adverse. Production going up, on the other hand, is a good thing, and energy intensity going down is also a good thing, so those are shown as green. So, moving on with our agenda, we'll turn to the detailed examples that I mentioned. And the first of these is the summer rainstorm. The specific example I'd like to talk about is distillation column performance and how summer rainfalls can affect that. We have people from many different disciplines in this webinar, so I must briefly explain that distillation is the most common method for taking a liquid stream that contains a mixture of chemical components and separating those components into separate streams. It does the separation by boiling the liquid at the bottom of the distillation column. The components that boil at the highest temperature remain as liquids and leave at the bottom of the column. Those that boil at the lowest temperatures go up the column as vapors, and they are condensed after they leave the top of the column. The column is hottest and the pressure is highest at the bottom, and the temperature and pressure are both lowest at the top. And the compositions of the liquid and vapor inside the column also change as you go from the bottom to the top. Now, let's consider what happens when there is a heavy rainstorm. In many distillation columns, the overhead equipment is not insulated, so the pipes and equipment are cooled rapidly by the rain. This increases the rate of condensing, which causes the pressure at the top of the column to fall. This, in turn, causes more material to vaporize inside the column and go to the top. This includes some of the material that is supposed to go to the bottom. Consequently, the overhead composition changes and it can go out of specification or off spec. and it may take many hours to get it back on spec. This often means that we have to reprocess the overhead product. In other words, distill it again to get it on spec. And then just to summarize this, when we have our rainstorm, we get an uncontrolled increase in the condenser duty. The pressure at the top of the column decreases rapidly. The liquid on the trays vaporizes more than it normally would, and this additional vapor goes to the reflux drum, and the composition of that vapor is not correct. It contains more of the heavier materials than we want in the distillate. So these heavy ends contaminate the distilled product, and so we are left with an off-spec material, out of specification, and this then has to be reprocessed. So what this means is that in order to get back to the composition that we wanted for our overhead material, we basically have to distill it a second time. We have to reprocess it. So the effect, if we go to this table that I talked about, is that the energy consumption goes up because we're having to distill this material twice over. Moreover, our production has gone down because time has been effectively wasted distilling this the first time. And so the overall effect is a double whammy as far as energy intensity is concerned, more energy consumption over a longer period of time, meaning that production per unit time has gone down. And so the energy intensity is significantly increased. All right, let's turn now to our second example, which is throughput cuts, or ways that we reduce the production in our plant by changing flow rate. And I'd like to focus on centrifugal pumps, which are one of the most common pieces of equipment that you'll find in most refineries and chemical plants. And specifically, I'd like to look at 3 different ways of controlling centrifugal pumps, which have different impacts on the energy intensity that results from flow reductions. The first type of control I'd like to talk about is generally called bypass control, although I personally prefer the term spillback control or even recycle control because I think it actually gives a better concept of what's really going on here. And the idea is this: you have a certain feed stream that you're passing through your pump. It comes out on the discharge side, and you take a portion of that flow to the downstream user of that stream. But the other portion you simply return back to the suction side of the pump through a spillback line. Now, many companies or many consumers like this design, this configuration, because it actually can give you a very stable and steady flow to the user. However, it does have significant disadvantages, as we'll talk about later. Another thing I should comment is that there are actually a number of different variations on this configuration. One of the most common I've seen is that I'm showing here that we take the spillback from the discharge side of the pump and return it directly to the suction line. But in many cases, the feed stream to the pump is coming from a feed tank or a surge tank, and the spillback line can go back into that tank. And that does have advantages. Most importantly, it provides additional stability to the flow. Well, here is a variant of the spillback or bypass control. We have now added a cooler on the spillback line. This is needed because when we pump a liquid, its temperature rises, and if the spillback becomes very large, that could result in overheating of the pump. Let's now look at the material balance here. We are trying to deliver a quantity of flow F to the consumer on the right-hand side of the diagram. On the left-hand side, we must provide that same quantity of feed, big F, on the extreme left-hand side of the pump. We're controlling the flow by adjusting the spillback flow, little f, and that spillback mixes with the incoming feed upstream of the pump to give a combined flow through the pump of big F plus little f. And when we look at this diagram, the flow little f simply circulates around and around. It does not contribute to the net flow through the process. And so let's suppose that we want to reduce the flow, big F, going to the downstream consumer. Well, we do that by opening the spillback valve, which means that little f must increase. Now, there's virtually no change in pressure at either the suction or the discharge side of the pump, and the pump speed is constant. So the flow through the pump, which is big F plus little f, also stays the same. Any decrease in big F must be equal to the increase in little f. Consequently, the power requirement or the energy consumption within the system remains the same. So if we look at our equation for energy intensity, we see that the energy consumption, EC, could go up or down by very small amounts, but it's essentially constant. And the production rate, which corresponds to the flow through the system, big F, goes down. So the effect is that energy intensity goes up. Well, now I'd like to show you a couple of other control mechanisms for pumps, flow control mechanisms. And the first one is what is called throttle control. And here we put a throttle valve on the discharge side of the pump in the discharge line. And as we close that control valve, so we throttle the flow goes down. And there will generally, when we do that, be a reduction in the pump power requirement. However, that reduction, the percentage reduction in the pump power, is almost always a smaller percentage than the reduction in flow rate and the corresponding reduction in plant production. So the net effect, the energy consumption goes down, production or flow rate goes down, and the energy intensity goes up. This is, however, better than the situation with the bypass control or spillback control, because we do at least get some reduction in energy consumption. The third example that we have is speed control, and this is usually accomplished with a variable frequency drive in the case of electric motors. Generally, an electric motor will run at constant speed, and so the pump speed will be also running at constant rate, constant pump speed, and so we have to use valves to control the flow. When we use a variable frequency drive, we can actually reduce the pump speed in order to reduce the throughput or the flow rate. And that then means that, yes, once again, energy consumption goes down as flow rate or production rate goes down, but in some cases, the energy intensity also goes down. In other words, the percentage reduction in energy consumption may, in some cases, be larger than the percentage reduction in flow or production. The example I showed you earlier with the bypass control or spillback control was taken from an actual energy assessment that was carried out a few years ago. The recommendation from that study was to add a throttle valve on the line to the downstream user of that material. And this then allowed a significant reduction in the flow going through the spillback line. And the savings were in the order of $150,000 a year, which was quite significant. You still need to have the spillback line available, however, because this is a mechanism for ensuring that the pump always has at least its minimum flow requirement and that it doesn't overheat. As I mentioned earlier on, that is a significant requirement in this situation. And this also raises a very important point. Whenever you try to change control systems, it's very important that you consider the safety implications and reliability implications of any changes that you make. Well, I'd like to turn now to talk about some other situations where we see significant increases in energy intensity due to changes in operating conditions. And I think the most significant example is shutdown and restarting of plants. While a plant is actually fully shut down, it's offline, there is no production. But even in that situation, there is always some amount of energy being consumed or wasted within the plant. So in that situation, we have our denominator going to 0 while there is a finite numerator. So of course, at that, in that particular period of time, the energy intensity is actually infinite. During the period when you're shutting down the plant and subsequently restarting it, well, that can take several days in some cases, but during that time we are consuming a considerable amount of energy. For example, during the shutdown period, you may be cooling down equipment in a controlled manner, and then restart, you may be reheating furnaces and other equipment, for example, using energy while you're actually making very little usable product. And you may also end up with off-spec product, as we discussed in an earlier example. This then has to be stored for subsequent reprocessing. And so the result is, even though your overall energy consumption may be less than it would be during normal operations, your net production is way down, and the energy intensity may not actually be infinite, but it's certainly much higher than normal. And I'd like now to talk about just a couple of other cases. So one situation is what you might call a partial shutdown, or often called a squat. And this is commonly used for maintenance activities or to recover from major plant upsets. And in this mode, certain pieces of equipment within a plant will be shut down. Other pieces of equipment will be in a standby mode, so they can be run at low load and put back into full production quickly while the rest of the plant runs. And so overall, you have a situation here where there's obviously some instability in the operation, but also you are producing significantly less product than you normally would from your plant. And the overall effect is an adverse impact on energy intensity. There are also many plants that make a multitude of different products or different grades of the same product. For example, polyethylene, there are many different grades of polyethylene. And whenever you change from one grade to another or one product to another, you will have to do some or all of the things that I list on the slide here. You may have to stop or start pieces of equipment, or maybe the whole plant in its entirety. You may have to change feedstocks or adjust temperatures and pressures and flow rates. And all of these will lead to some disruption to the operation. And as we've seen from previous discussions, this will also lead to an adverse impact on energy intensity. Well, how does all of this apply to Hurricane Harvey? I think it's fairly clear that pretty much everything we've discussed does have an impact in situations like hurricanes and other major disturbances from natural causes. For example, we talked about rainstorms and their impact earlier on. Clearly, when a hurricane comes in, you get rain. You will also have to stop equipment or put equipment in standby mode. But typically with a hurricane, most plants will end up being shut down to protect them and to protect operators. And there will then be an extended period being offline and then restarting. And as we saw from our discussion of plant shutdowns, these activities all lead to an adverse impact on energy intensity. And then even when you come to the final startup of your plant, with a hurricane like Harvey, there is some disruption to the surrounding society, the surrounding infrastructure, and this can result in cuts in your throughput or instability of operation because of problems in the supply chain. And so this also will have a significantly adverse effect on energy intensity and energy efficiency. Well, what can we do to mitigate against these problems? Well, obviously, it's a whole different story dealing with a small disturbance in flow rate or composition in the normal operation of a plant and dealing with a hurricane, very different situations. And so not everything that I list on this page is ultimately going to be useful to you in a hurricane, but it will tend to be helpful in general in improving the resiliency of plant operations. And there are a number of different areas to look at. We can consider the design of our plant. We look at operation, and then also we need to consider external issues outside of your battery limits and the overall infrastructure and environment in which you're operating. So on the design side, the better insulated equipment is, the more resilient it is against fluctuations in external temperatures and rainstorms, as we saw in the example of the distillation column earlier on. Surge capacity within surge tanks, feed drums, product drums, and so on can help to deal with changes in flow rate and composition. And there are ways that control systems can be improved also to manage disturbances. From the operational side, we talked about plants where we change grades or products, and the less often we make those changes, the less disturbance there is. And so if you can go for longer runs with each product or each grade and fewer transitions between them, so you will tend to improve the energy intensity of your process. Also, when it comes to shutting down and starting up processes, there are often steps included in those procedures that are actually unnecessary or can be shortened. And if you can make the startup and shutdown activities quicker, then in general you'll have shorter unstable times, and therefore you will improve your energy intensity. Having said that, we have to be very careful with changing operating procedures, because once again, we do have to be very conscious of process safety and equipment integrity, and be very careful not to go outside the safe operating envelope of your process. And finally, something that most of us as engineers typically are blindsided by, we're not only dealing with our own process, we have to consider the surrounding infrastructure and supply chain, and the resiliency of that whole structure is very crucial, especially in situations like hurricanes, where the whole of a region is going to be affected by the disturbance. And then effective emergency management within the emergency situation, like a hurricane. The better that emergency management and the quicker things can be brought back on stream outside of your battery limit, the less your downtime is going to be. And that really is the subject of the next talk that we're going to have. Well, that brings me to the end of what I wanted to say. I do list here some references. The distillation material that I talked about earlier comes from my colleague Charles Herzog, and the data on the impact of Hurricane Harvey came from the article listed there by Laura Cassidy. And also I do have an article in press with chemical processing, which is due to come out in June. And so with that, I will end, and happy to take your questions. Okay, so I have received a couple of questions. If anyone else would like to send me a question, please put it in the chat and send it specifically to me, Alan Rossiter. So just one moment here. The two questions that I have so far, have you ever applied energy intensity as a metric to improve energy efficiency in operations? And the short answer would be yes. Very often I have seen energy intensity, the amount of energy consumed per unit of production, used within various energy management programs as a mechanism for tracking performance and driving efficiency by identifying the conditions that improve energy intensity. So yes, and it's also used as a design parameter too in many cases. The other question that I've seen thus far was related to throttling. And the question was, how can you be saving energy when you throttle the discharge of a pump? And I guess the short answer is you don't really save energy. What you do, though, is that you do reduce the energy consumption of the pump, typically, because the flow rate goes down. And the biggest contributor to the energy required in pumping is related to flow. What you also do is you push the back pressure up on the pump, and that obviously tends to increase energy. And there are one or two other factors like pump efficiency that come into play as well. But the overall effect in most cases when you reduce the flow by throttling, at least a relatively small amount of throttling, is that you reduce the overall energy consumption by the pump. So I'm looking to see if there are any more questions here. And you may continue to send questions if you have any. But what I will do for the moment is just to roll into, first of all, just a reminder about the certificates of participation. If you have a need for a Texas certificate, please send a text message to Lee Lopez with your name and the email address. And I also put a message into the chat system for everyone. If you want an out-of-state certificate, there are some additional requirements, and you'll need to send an email giving additional information to Lee at her email address. And as I said, also for questions, Q&A, if you have any questions, either from the presentation you just heard or from the next couple, please let me know through the chat system. All right, as I mentioned at the start of the webinar, we were expecting Commander Joe Leonard to be joining us at this point. Unfortunately, he is he is an emergency management consultant, and unfortunately he is dealing with emergencies, and given what's going on at the moment around us, that's not really surprising. He said he would try to join us at the end of the session, at the end of the webinar, but he did not think he would be able to. So if he does come in later, we will introduce him to you and get him to at least give some of his talk. But for the moment, we just wish him well with all his work in managing the emergency in which we currently share. I will, however, show you a few of his slides. There are a couple of things here that I think you will find interesting, and there are also a couple of videos that are included, so they won't require much explanation. But those of you who were listening to my Harvey story at the beginning of the presentation I gave will recollect that I talked about houses that looked as if they were standing on the side of canals as I was flying into Intercontinental Airport after Hurricane Harvey. And I happened to notice when I was looking through Commander Leonard's material that he actually had a picture of exactly those houses, which unfortunately I was not able to take while I was flying in. However, let's just move forward on these slides and I'll see if I can show you his videos. Except the slides are stuck. So I'm going to have to come out of this for a moment. Oh, here we go. Looks like I'm going to have to come out of this for a moment to advance the slides. All right, so this was just listing severe weather events. But now we come to, I think,
Harvey was different because it challenged us in every way possible. Our major facilities in the storm-impacted areas were essentially isolated because of floodwaters. Coast Guard men and women across our service and at every level displayed remarkable initiative and innovation, overcoming many, many obstacles.
We were able to get in that morning prior to sunrise, and due to the low ceilings, we were having to fly at times as low as 100 feet, flying in between light poles on highways, flying over power lines.
The day always started pretty early. We would have our morning meetings to figure out what we're going to do that day, where we're going to try to get to.
Coast Guard, anyone out here?
And then we were out on the water the rest of the day, wading through water that was chest high. And we stayed out till 7, 8 o'clock at night, dry off, and go to bed for the night to get up and do it again the next day.
This was a high-risk operation. They are saving lives in the middle of tropical storm force winds and torrential downpours.
Our main mission was to protect the asset. We left the pier and anchored out in the Houston Ship Channel, dropping both of our anchors and two 12,000-pound sinkers over each side of the buoy port on our ship.
We were taking upwards of 1,000 calls per hour. There were more than 26,000 calls received.
What we would end up doing is going out, picking up as many folks as we could until, by policy, they were no longer allowed to even keep flying. So people were really pushing their limits. But one thing I'll never forget is looking back in between hoists and seeing young children as young, sometimes as 5 or 6 years old, or even babies, getting hoisted up in baskets, and looking back and see our flight mechanics and rescue swimmers taking care of them and comforting them when they were in a really terrifying situation.
More than 100 Coast Guard families lost their homes to the floodwaters or to the winds, but every one of those responders there had their family back home and operated through the uncertainty. It's an amazing sacrifice for our crews to be fully engaged in a rescue operation, even while they're wondering about their families back home.
I was born and raised in South Texas, so I'm not far from home. And while the other buoy tenders coming from D8 and D7 that came in to help us work on our aids to navigation, that gave us time to check in with our families and our houses to make sure everything was okay. So it was definitely something that I'm not going to forget about.
There was a young mother who had attempted to drive away from her flooded neighborhood, but became trapped in her car and had to climb on top of her car with her baby. We were able to launch an asset out there to go get her. So that one has stayed with me and will stay with me forever.
Our shallow water rescue craft assisted or saved close to 10,000 people. But when you think about the number of rescues that they directed, our junior petty officers in these boats would move into a flooded neighborhood, and because the boat said U.S. Coast Guard on the side, they were in charge. Local responders, state responders, Cajun Navy responders would come to our people and say, tell us what to do. Our petty officers would establish search grids, they would establish landing zones, and they would lead teams into flooded neighborhoods. And in that way, those junior Coast Guards, men and women, directed the rescue of probably 50 or 60,000 individuals.
The reason I joined the Coast Guard was to help people, and it just made me really proud to be a member of a service that goes out to help people first, and that is our highest priority.
We're talking about the Coast Guard heroes of Harvey, and there are many of them, and they're across our organization. They include our active duty, our reservists, our auxiliaries, our civilian employees. But there is the Coast Guard Foundation that helps the heroes, and I will tell you the foundation was in my office in New Orleans even while the storm raged in Houston, asking how they can assist Coast Guard families impacted by the storm. That provides peace of mind that allows our Coast Guard crews to do the work that they do.
So I have to say, Commander Leonard was part of that team, and so I'm very glad he was. We were at least able to see that ready acknowledgement of the work that they did during Harvey. And also, I'd mentioned that picture of the houses that looked as if they were along the canals. You saw it in that video, and I think you see it again here in the picture on the bottom right, bottom left side here. So again, memories of Hurricane Harvey. And I believe there was actually another video. These pictures, of course, all showing aspects of the activities that they went through back during that period. But I think there is another video at the end, in which case we will run that as well. One thing I noticed that as part of their training, they included certified energy managers alongside emergency managers. And so we see, certified emergency managers, yes. Similar to energy managers, but emergency managers in this case.
When Harvey formed in the Gulf of Mexico, Coast Guard crews worked around the clock to ensure the safety of our people, assets, and facilities, to direct actions in order to minimize the risk to commercial ports, and to prepare for the search and rescue missions that we knew were to come. Even before Harvey made landfall in South Texas, Coast Guard air crews rescued a dozen mariners from the motor vessel Gulf Justice as she was aground and foundering in high winds and heavy seas at the leading edge of the storm. Harvey raged on for the next 5 days, and Coast Guard crews and aircraft and shallow water boats battled tropical storm winds and near zero visibility in a treacherous urban environment to rescue stranded victims, many of whom suffer from serious medical conditions and needed immediate treatment. And while our Coast Guard crews directly affected the rescue of more than 11,000 people in that time period, using our facilities, our command and control capability, and the on-scene initiative that defines our enlisted workforce, Coast Guard men and women directed and facilitated the rescue of tens of thousands. Even before the storm cleared Texas, our crews were on the water, working with partner agencies to restore critical channels and aids to navigation, and to ensure the port facilities were able to safely receive ships and start operations here in the Port of Houston and throughout Texas. Those efforts ensured that the area refineries not severely damaged by the storm were able to receive feedback and continue to operate. In the weeks and months following the storm, Coast Guard women and men responded to more than 670 pollution sites and removed over 58,000 gallons of oil and more than 8,500 pounds of hazardous material that were spread through coastal Texas by the storm and the floods. As the commander responsible for Coast Guard operations in a 26-state region, including all of Texas, I'm tremendously proud of what our Coast Guard men and women accomplished in the face of this historic storm, even while many of them suffered damage to their own homes and property alongside their fellow Texans. Mr. Chairman, members of the committee, the men and women of the 8th Coast Guard District are proud and privileged to be members of the world's greatest Coast Guard, and we appreciate your continued strong support of our service. We continue to stand with Texas alongside Texans, ready for whatever comes next.
I just want to thank all 4 witnesses and who you represent and everybody in the room who is a part of the response and recovery effort for your service to not only this nation, but to this great state of Texas.
All right, and yes, we certainly acknowledge the great work that was done by all the emergency responders during Harvey. One thing that I did discuss with Joe in preparation for this session was the aspect that a lot of what they did during that period was not simply to rescue people, but also to help restore the infrastructure of the whole region. And I mentioned earlier that disruptions to infrastructure often lead to delays in startups or long periods of running with disrupted supply chains. And that was an important part of the recovery from Harvey as well. Had it not been for all the work done to restore and resuscitate, if you like, the infrastructure around the area, there would have been much worse impact on supply chains and therefore a much worse impact on production and energy intensity within the industrial sector. Let's just go to the end of these slides quickly. And so I think a lot also of Commander Leonard's message was the can-do attitude that enabled the Coast Guard and the other emergency responders to get things done.